This lesson is on the fundamental counting principle. To introduce the fundamental counting principle, I'm going to start by going over tree diagrams. A tree diagram is a simple way to show all of the possible outcomes of a sequence of events or really choices. Let's look at example 1 to go over this. When you get ready for school, you find the following options of clean clothes you can wear: a red, blue, or white shirt, jeans or shorts, tennis shoes or sandals. Draw a tree diagram to show all of the possible outcomes. In a tree diagram, each level is like a decision you are making. So the top level is going to be my shirt. I can choose whether I want to wear a red shirt, a blue shirt, or a white shirt. So I'm going to line those up using letters to abbreviate for each of those. Off of each shirt, you can pair those with what? Well, the red shirt can be worn with jeans, or the red shirt can be worn with what? Shorts. You're only going to pick one shirt to wear. You're only going to pick one bottom to wear. But if you wear the blue shirt, you can choose to wear it with jeans or shorts. If you wear the white shirt, you can also choose whether you are wearing jeans or shorts. So see how I have it lined up. The top level is my choice of shirt. The next level is my choice of bottom. I have one more decision to make, so I'm going to have one more level here. If you were choosing 5 things, you would have 5 levels. So the first option, the first outfit here is a red shirt with jeans, and off of that I could wear tennis shoes, or I could do the red shirt with jeans and sandals. You're branching off. Look at each path that you have created. Right here, this first section are all the outfits with red shirts, right? Look at each line. Start at the top and see basically how many different ways you can trickle down. Red jean tennis shoe, red jean sandal. Red short tennis shoe, red short sandal. So there's 4 paths there. There's 4 outfits. Let's keep going though, because I could wear the blue with jeans with tennis shoes, or the blue with jeans with sandals. I could wear the blue shirt with shorts and tennis shoes, etc. You probably get the point by now. A tree diagram helps you to see all the different outfits that can be created. Really, all you do is look at the bottom here. You're looking at the number of paths you have. So we have 1, 2, 3, 4 paths there, and then we can keep going. We have 5, 6, 7, 8 paths there, and then we keep going. We're adding on 9, 10, 11, 12 paths. What does this mean then? This means that there are 12 outfits that can be created. Really, I should write that down below here. So the next question was, how many outfits are involved with choosing a red shirt? Well, when I look at these, how many outfits have red shirts? 4. 4 outfits have a red shirt. What is the probability of choosing an outfit with a red shirt? Remember, with probability, we can set it up with this probability notation here. And to find the probability, you're going to divide how many outfits have what you want, a red shirt, 4, by the total number of outfits that could be created, 12. Those were the paths from your tree diagram. 4 twelfths can be simplified, so we wouldn't leave it like that. 4 divided by 12 reduces to 1/3. If you do the division, you would get a repeating decimal. It's 33.3 repeating percent. Now, a tree diagram isn't bad here. There's not that many paths, but let's say you were making 10 different decisions and each category had 5 or 6 options. That would take you a long time to create a tree diagram. So mathematicians were always looking to be efficient. We found something else that makes this a lot quicker: the fundamental counting principle. The fundamental counting principle says if there are m ways to choose a first item and n ways to choose a second item after the first has been chosen, then there are m times n ways to choose all items. In the first example that we just did, we were choosing outfits. We have to pick a shirt, we had to pick a bottom, and we had to pick a shoe. So it's almost like you have three decisions, not like, you have three decisions you are making. Well, how many options did we have for the shirt? We had 3 different colored shirts. How many options did we have for the bottoms? Remember, you could only wear jeans or shorts because those were the only things that were clean. So we have 2 different options for the bottoms. How many options did you have for shoes? Also 2, tennis shoes and sandals. And what we found is when we multiply the number of options for each choice, we get the total number of outfits. 3 times 2 is 6, times 2 is 12. So the fundamental counting principle shows us very quickly how many total outcomes there are without doing a tree diagram. It's nice. Okay, let's try the next one. TGI Fridays is offering a 3-course meal for the low price of $20. If there are 5 appetizers, 8 entrees, and 4 desserts that you can choose from, how many different meals could you order? So to set these problems up, I like to kind of set up a slot or a line to represent each choice. So we are going to choose an appetizer. We're going to choose an entree. And you could abbreviate this. You could use A, E, and we're going to choose a dessert. I'm writing it out for the first one to help you. You're really just labeling the slots. It's just showing me your work. You could also just label it A, E, and D, and I'll know what those are. So how many options do you have for appetizers? Well, there are 5 different appetizers on this special menu that you can order from. How many options for the entree? 8. How many options for the dessert? 4. Put the multiplication dots in between because you are multiplying these together. How many different meals could you order? Well, 5 times 8 is 40, times 4 is 160. So there are 160 different meals. Let's always put a label on our answer that could be created when you're choosing one of each category here. See how much quicker that is than writing out the whole tree diagram. Now, if it tells you to write out a tree diagram or it asks you to list all the different outcomes, then you have to show me the outcomes. We didn't list the outcomes here. We just know that there are 160 total outcomes, right? Okay, so let's see really more where this is used. The numbers can get a lot bigger, especially very quickly. A good example of this would be license plates. The PA license plate has 3 letters followed by 4 single-digit numbers. So I want to know if the same letters or numbers can be repeated, how many unique plates can be made. You know, my license plate cannot be the same as your license plate, so they have to be unique. The license plate have to be long enough, you know, so that they could come up with a large amount of different plates to satisfy all the people in the state. Okay, so again, you have to think about how many different kind of decisions you're making. Well, a license plate has 3 letters. So I'm going to label these letter, 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 followed by 4 single-digit numbers. I'm going to use D for digit. You could use the number symbol as well. So I should have 7 slots because there are really like 7 different decisions made in your license plate. Now, a key thing here, it says, I don't know if you caught this, it says the same letter or number can be repeated. That's going to make a difference here. So to figure out how many license plates can be created, you have to think, how many letters are there in the alphabet? How many letters do we have to choose from in the alphabet? Hopefully you guys know this. There are 26 letters in the alphabet. Since the letters can be repeated, there are 26 different letters that could be in the first spot, 26 different letters that could be in the second spot, and still 26 different letters that could be in the third spot. My license plate could be AAA at the beginning, or AAB, or ABB, or XYZ. We could keep going. It would be very hard to list all of those. That's why this fundamental counting principle is really nice. So far, we know it's 26 times 26 times 26. Now, the last 4 spots on the license plate are 4 single-digit numbers. So how many options do I have for a single-digit number? If you said 9, You're incorrect. See, it could be a 1 or a 2 or 3 or 4, 5, 6, 7, 8, 9. So why are you incorrect? You forgot 0. 0 could also be a number on your license plate. So there are actually 10 single-digit numbers. Since the numbers can repeat, the 10 is the number of options you have for each of those decisions. Don't forget to go back and put the multiplication dot in between. Show me that you are multiplying. That is the fundamental counting principle. Okay, so this is going to be a really big number. I want you to get out your calculator and put that in. Type in 26 times 26 times 26 times 10 times 10 times 10 times 10, or basically times 1,000. This is a huge number. We could create 175,760,000 license plates that would be unique to each other. Before, they would have to be the exact same. That's amazing. Awesome. Okay, let's try the next one. If the same letter cannot be repeated this time, let's think about how that's going to change the problem. The letter cannot be repeated. I want to know how many unique license plates can be made. Okay, so we still have the same setup for a license plate. The license plate still has 3 letters followed by 4 digits. So set up your slots. Label those slots. This is not an option, guys. We want to see your work. We want to understand your work. By labeling it L, I know that's standing for letter. By labeling it D, I know that's standing for a digit. Okay, but this time the same letter cannot be repeated. So your first letter, there are 26 options, but something had to be chosen. Pretend an A was in the first spot. How many letters now do you have for the second option if the letter can't repeat? Right, 1 letter is taken already, so you only have 25 options now for the next letter. But if the letter can't repeat again, take 1 away, 1 more. Now you have 24 options left for the third letter. The digits didn't say they couldn't repeat, so I'm assuming the digits can repeat. There would be 10 options, 0 through 9, for each of these. It's the fundamental counting principle. We are multiplying. Please add in those dots to show me that you are multiplying these number of options. Okay, again, this is going to be a huge number. 26 times 25 times 24 times 1,000 on your calculator. Type that in. Don't wait for me. You do it. You check it. Did you get 15,600,000 plates? It should be less than the first one, right? Because since the letters cannot repeat, we should have less options here. Awesome, this looks great. Okay, so let's try one more and let's connect this back to probability. Assuming the letters and the numbers can repeat, I'm going back to that same problem. Where did the letters and numbers, where were they allowed to repeat? Guys, that's the same as A up here, so we already did that right here, okay? Assuming that the letters and numbers can repeat, find the probability this time that a license plate has the first letter as a letter A. Okay, so this is going to take 2 steps here. First, we need to find out how many plates have the first letter as an A. So this time, I'm going to label that A, and then any letter, and then 4 digits. Well, guys, how many options do you have for the first letter being A? In the alphabet, how many A's are there? Just 1. But the letters and numbers can repeat, so there are 26 options for the second and third spots. The numbers can repeat as well, so I'm just going to put times 10, times 10, times 10, times 10. What am I finding right now? This is representing the number of license plates that have a letter A first. When you put that in your calculator, did you get 6,760,000? Now those are the plates with an A first. Okay, so the second step then is to find the probability that a license plate, let me move this up a little bit, get myself more room. Find the probability that a license plate has the letter A. Remember what probability is. Probability that it's the first letter, A, is going to be, in the numerator, how many plates have a letter A, and in the denominator, how many plates can be created. If you're smart about this, you'll realize you already found both of those numbers. How many license plates have the letter A? 6,760,000. That's the number we just found, have the letter A. You're dividing that by the total number of plates that can be created if the letters and numbers can repeat. Do you remember what that was? That's from A, guys. That's your answer in A. So it's 175,760,000. Divide that to get your percent. Let's round to the tenths. My class rule is generally that we round to the tenths if it doesn't specify. Probability, we often like it as a percent. You could leave it as a reduced fraction as well. This is hard to reduce. I'm going to divide that in my calculator. The numerator divided by the denominator, and then times 100. Are you looking at that decimal? Round it. It's about 3.8% is the probability that a license plate will have the first letter as an A. So try a few more of these. Try your homework. Practice the fundamental counting principle. Hopefully it makes these problems nice and easy for you. If you have any questions, ask your teacher.